A floor consists of 150 mm thick slab monolithically constructed with 300 mm wide beams spaced at 3.6 meter center to center spacing. The effective span of beams is 5 meter. The slab is subjected to superimposed load of 5 kN per meter square. Now design an intermediate beam of flexure. Use M20 concrete and Fe415 steel. Okay, so first of all, let's check which data is given in question. BW, width of web, is 300 mm, that is given. Effective span of beam, that is L, is 5 meter. Now live load or superimposed load is 5 kN per meter square. FCK is 20 Newton per millimeter square for M20 grade of concrete, and Fy is 415 Newton per millimeter square for Fe415 steel. Now we have to find out effective width of the flange first. For effective width of flange as per IS 456-2000, we have to use this formula. BF is equals to L0 by 6 plus BW plus 6DF, which is equals to 5000 by 6 plus 300 plus 6 into 150, that is equals to 2033.3 mm. So as per question, the diagram will be like this. 300 mm is width of web, center to center distance is 3.6 meter, and 5 meter is length. This is the plan, and this is the cross-sectional view of typical T-beam, which is monolithically constructed with slab. Okay. Now available flange width is 3600 mm, which is greater than 2033.3. Now effective width of flange BF is 2033.3 mm. Now assuming depth of beam as L by 12 as for the assumption which is discussed in first lecture of T-beam, which link is given below. So that is equals to 5000 by 12, say 400 mm. So depth capital D is 400 mm. Now effective depth is small d is equals to 400 minus 30. We assumed effective cover as 30 mm. So effective depth is equals to 370 mm, and depth of web is 400 minus 150, that is equals to 250 mm, except the width of depth of flange. Now we have to calculate load, the load calculation part. Design load of slab is 0.15 into 25, that is equals to 3.75 kilonewton per meter square. Now superimposed load is 5 kilonewton per meter square, which is given. So total load on slab will be 3.7 plus 5 plus 5, that is equals to 8.75 kilonewton per meter square. Now load from 3.6 meter width of slab is transferred to the intermediate beam. Now load transferred from slab to beam is equals to 8.75 into 3.6, which is equals to 31.5 kilonewton per meter, and self weight of web is equals to 0.25 into 0.3 into 25, that means the depth of web is equals to 1.875 kilonewton per meter. So total load on the beam will be 31.5 plus 1.875, that is equals to 33.375. Okay. Now maximum bending moment on beam for simply supported beam is WL square by 8, that is equals to 33.375 into 5 square by 8, that is equals to 104.3 kilonewton meter. Now you have to make it factor bending moment by multiplying load factor. So mu is equals to 1.5 into 104.3, that is equals to 156.5 kilonewton meter. Now assuming the neutral axis lies on flange, as I told in earlier lectures also for T-beam, for consideration, first of all we assume always the neutral axis lies in flange portion. So for that, XU is equals to 0.87 Fy into AST by 0.36 FCK into BF, that is equals to 0.87 into 415 into AST by 0.36 into 20 into 2033.3. So XU is equals to 0.0246 AST. Okay, so this is the value of XU. Now for an under-reinforced section, mu is equals to 0.87 Fi AST into d minus 0.42 XU. So here mu is 156.5 into 10 to the power 6 is equals to 0.87 into 415 AST within bracket 370 minus 0.42 into 0.0246 AST. So from this we can write 156.5 into 10 to the power 6 is equals to 133,588.5 AST minus 3.739 AST square. By solving it, we get AST is equals to 1213 mm square. So XU is equals to 0.0246 into 1213, that is equals to 30 mm, which is obviously less than 150 mm. Hence our assumption that neutral axis lies in flange is valid. Okay, so we have to solve the rest part of problem for this condition. Now using 30 mm diameter bars, area of one cross sectional area of one bar A5 is equals to 314 mm square. So number of bars is equals to 1213 by 314, which is almost equals to 4 bars. So that is equals to, that's why AST will be 1256 mm square. Now minimum area of tensile steel AST minimum is equals to 0.85 BD by Fy, which is equals to 0.85 into 300, that is B, into 370, that is D, by 415, that is Fy, that is equals to 228 mm square, which is less than 1256 mm square. This is minimum area of steel required, so hence the design is safe with respect to this. So maximum area of tensile steel is 0.04 BD, that is equals to 0.04 into 300 into 400, that is equals to 4800 mm square, which is greater than 1256 mm square. So area of steel provided is lies between minimum area of steel required and maximum area of tensile steel required. So hence the design is safe. Okay, that's all for this lecture. Thank you.